switch gears a little bit and try to put together a common model involving mutation, selection, and genetic drift, and try to understand what the data tells us about the intensity of these processes. And the question we will be asking is how to tell Darwin from Kimura. So how do we know if how much of the evolution has been adaptive, has been due to fixation of advantageous mutations, and how much of the evolution has been neutral? So the neutral theory of molecular evolution has been famously put forward by Mora Kimura in early 1980s. So this is the paper in Nature that he planned. Actually, that was an earlier paper in 1968, whereby he claimed that if we just count the numbers of nucleotide substitutions between species, this number turns out to be so large that it involves too high a lag load. So we have discussed with you that the mutations, the adaptive mutations, cannot be fixed at any rate. There is an intrinsic limit on how rapidly selection can fix novel adaptations. So Mora Kimura has been using this logic to say, well, look, human and chimpanzee have only diverged about 8 million years ago, and we see that they have accumulated already 1% of their substitutions. 1% of their sites have already acquired substitutions, and that's a huge number of substitutions. So that's what, about 30 million substitutions, and so they had to proceed at the rate of about 3 substitutions per year. And if we just do the math, it turns out that that's just too high a rate of adaptation. Now his reasoning was wrong, because he was assuming that the genome is packed with functional sites that are way more genes than there actually are, and that so he was assuming, for example, that there are several hundred, if I remember correctly, genes in several 100,000 genes in our genome. In reality, much of our genome is, of course, neutral, is, of course, non-functional. His reasoning was wrong, however, his conclusions were correct. This was the first paper which put forward this neutral theory, this neutral explanation for the divergence. He was saying, well, if these mutations, if it's impossible that all these mutations have been adaptive, then many of them have been neutral. And there was at about the same time, there were these guys, Ken and Jukes, which came forward. This is the same group, so the Jukes-Cantor model, who have used different reasoning, coming up to the same conclusion, saying that most evolutionary change in proteins may be due to neutral mutations and genetic drift, and not to adaptive mutations as claimed previously. And of course, this title, non-Darwinian evolution, has been rapidly, picked up by creationists and people trying to attack the evolutionary biology. They were now saying, well, you see, when the evolutionists cannot agree among themselves if evolution is Darwinian or not. And that was to an extent true. This was the well-grounded and I think probably the most real, the most actual attack of pure Darwinism since its origin. Indeed, it turned out that much of the evolution was non-Darwinian, as we will see shortly. However, this, of course, has nothing to do with the fact that evolution has taken place. That is uncontroversial. Now, we are trying to understand how reality, what the reality tells us about the relative contribution of different forces and the parameters characterizing these forces in past evolution. And in theory, well, we do have some microevolutionary theory, we have a model, and for each set of parameters we can produce some kinds of predictions. However, the problem, of course, is that the data does not allow us to distinguish between different alternative models. We have combinations of models and their parameters which can lead to exact same pattern in polymorphism, exact same patterns in divergence, and therefore will be very hard to distinguish between. And this was indeed the case in the fight between the neutralists, the followers of Mori Kimura, and then of Tomoko Ota, and the followers of selectionists, the followers of the idea that the majority of evolution was still subject to selection, in particular to positive selection, people such as John Gillespie and others. And so there was this huge neutralist selectionist debate developing in the 1980s, 1990s. And we will talk about how it has developed briefly, but basically it turned out that many of the results that the selectionists used as support of the Darwinian evolution and seemed, to provide evidence for the selection acting throughout the genotypes, turned out to be equally compatible with the neutralistic worldview in which only a handful of mutations are adaptive, but the vast majority of novel mutations that arise and are fixed are neutral. So consider variation. In the selectionist worldview, variation is due to balanced selection favoring some of the alleles, and we have sort of discussed how that is not quite a viable explanation right now, but people did not know that yet back then. In neutralism, the variation arises naturally as a transient state of the evolutionary process. So the variation is just a stage in this process of novel mutations arising, and some of them going extinct, some of them fixing, because we have discussed that under neutrality these mutations can persist for rather long periods of time. The polymorphism can be maintained that is pretty high, and so if we come into the population and measure the variation at each particular instance, we can get huge variability that has nothing to do with selection, that has to do with just the random and unselected mutations being driven up and down by genetic drift. Divergence between species was explained by positive or directional selection by the selectionists. In the neutralist worldview, it is just a result of neutral evolution, of fixation of neutral alleles. Moreover, it turned out that many of the facts, that some of the facts accumulated by that time were consistent with the neutralist worldview and not so consistent with the selectionist worldview, such as this uniformity of the rate of evolution between species. That is something that is immediately predicted by the neutral theory. However, it is not quite clear why the rate of selective evolution should be constant over time, right? because there's no a priori reason to think that the fitness landscape, for example, will change at a uniform rate. Maybe it will, maybe it will not. That's not something that follows from any kind of theory. We have no theory for the rate of change of selected landscape. And so basically the question goes down to this. If we have a little replacement, say from small a to capital A in the course of evolution, it can arise under one of the three scenarios. It can either increase fitness, decrease fitness, or keep the fitness invariant. And what we're trying to understand is, well, leave alone individual substitutions, what is the overall frequency of events of each of these types in the evolution of species. So we have the so we have the equation for the dynamics for the fixation rate of novel mutations that are neutral. We can also write the equation for the fixation of the mutations that are selected and advantageous. And as the probability of fixation of each such mutation is approximately equal to S, so then the rate of fixation of such mutations overall will be now this. So now again we have to multiply the rate at which mutations arise, and that is n times u. Of course, the rate at which a mutation arises does not depend on the selection in its favor or against it, right? This selection does not know anything about this mutation, about whether it's good or bad at this stage yet. But then each such mutation will be fixed with some probability equal to its selection coefficient. Well, we can write out this more comprehensive equation that will cover all cases, no matter what selection is. But for moderate strength of selection, this will be the equation. So now under selection, the rate of fixation will be dependent on lots of different things, not just on the mutation rate as per the neutral mutation, but on the selection and also on the population size. Importantly, this rate will be higher if the population size will be higher. The intuition between that is that if novel mutations arise all the time at some rate n times u, if we have more mutations that have a chance to fix in the population under adaptation, then the overall rate of fixation of such mutations will be higher. So the more shots we take, the higher the probability that one of these adaptive mutations will fix eventually. So then we are left with this dichotomy between this rate of fixation and this rate of fixation. This is something that's predicted neutrally, and this is something that's predicted under selection. And we can ask, well, in what domain of parameters will the evolution be predominantly driven by selection, and in what domain will it be predominantly driven by neutral mutations? And this is just a reformulation of the above. So if selection on average is larger than the reciprocal of the population size, so then this parameter becomes larger, and the bulk of the mutations that will be fixed will be caused by selection. If, on the other hand, the selection is weaker than 1 over n, then the drift will be will dominate evolution. And one can think about that as the force that dominates evolution, but also one can think about that as the probability of fixation of an individual mutation that is advantageous. If an advantageous mutation has a fitness larger than the reciprocal of the population size, it will get fixed with a probability, with a high probability. If it is substantially less frequent than the reciprocal, less fit confers substantially lower fitness than the reciprocal of the. If its advantage is lower than the reciprocal of the population size, then the drift will likely override this mutation and it will not spread to fixation just because the selection was not strong enough. So such mutations will be referred to as efficiently neutral. They are not neutral, but their selection is not strong enough to override it. Sorry for the red print here, but basically that immediately tells us, suggests a way to distinguish between positive selection, neutral evolution, and negative selection at the rate of entire, like comparisons of entire chunks of genomes or genomes. We can compare the rate of evolution at sites that we believe are important, for example, some functional genic sites, and compare that with the rate of neutral evolution. And that will allow us to understand what type of selection acts or predominates in these functional, for example, genic sites. If the rate of evolution is higher in the functional sites than in some neutral sites, some sites that we a priori think that are neutral, for example, intergenic regions or something like that, then positive selection predominates. Then many of the substitutions that get fixed are actually advantageous. If these two rates are similar, then we can't tell much. The genes evolve at the same rate as the neutral sequences. We cannot tell much in that case. Finally, if the rate of evolution is much lower in genes than, say, in the intergenic regions, then negative selection predominates, which prevents substitutions from accumulating. And if we look at the real data, it turns out that nearly in each instance, the rate of evolution of important sites is much lower than that expected randomly. So this is an example of the data. This is on the vertical axis. This is the number of substitutions per nucleotide sites per unit time. And these are different categories of sites. And what you see is that the sites that are evolving most rapidly are the sites in pseudogenes. That is, the sites that we are pretty sure are not doing anything of importance. And all the other categories of sites evolve more slowly, and the more important a category is, the more slowly it evolves. For example, the fourfold degenerate sites in coding sequence that do not affect the encoded amino acid evolve pretty rapidly. Introns evolve pretty rapidly. The untranslated regions are evolving more slowly, and we know that there are some regulatory sequences in these regions which are frequently functional. And the sites that are non-degenerate, that is, such sites that in which any substitution which will change the encoded amino acids are evolving very slowly. So this is something that we are sort of already very used to, right? We sort of are used to the fact, those of us doing genomics and bioinformatics at least, are used to the fact that the conserved sequences, the important sequences tend to be conserved. However, this is quite a non-Darwinian view. This is not probably what Darwin himself would have imagined. Because Darwin himself has thought of evolution as a process leading to adaptation. Thought of selection as a process leading to adaptation. Here we see that selection is the force that primarily preserves the status quo, that primarily keeps the things as they are. And the negative selection is the predominant form of selection, and positive selection, well, we don't see any of it immediately, right? We do not see that some categories of sites evolve, functional categories of sites evolve at a very strongly elevated rate compared to the neutral rate because they're adapting so rapidly. This is something that we do not generally see. The importance of negative selection has been understood much later than Darwin. Ivan Fedorovich Malgausen, a Russian evolutionary biologist prosecuted in the Lysenko times, was, I believe, one of the first people, if not the first, who actually understood that that's the stabilizing selection, negative selection, is the predominant force in evolution. And there are other ways, the other types of data that we can use to see the same. So, for example, we can have the alignment of different species, here mouse, rabbit, human, and chicken, and look for the blocks, the segments in this alignment that are conserved. And if we see something that is well conserved between several species, that usually means that this segment is functional. And that works so well that people actually can annotate functional regions based on this logic. That is something called phylogenetic footprinting. So that was a very popular technique, and it still is a popular technique. If you think that some region of DNA is doing something, you usually go to the UCSC genome browser or some other genome browser and look how conserved that region is. If it is conserved throughout the, say, vertebrates, then that is plausible. If it evolves at the same rate as the surrounding nucleotide sequence, the near neutral rate, well, maybe it's not that important after all. And again, so here's a plot. There are many such plots. This one just happens to be from a paper, one that I did. So here there are several different yeast species, and I'm comparing the divergence between Saccharomyces cerevisiae, the model yeast, and these other species. And as you see, they cover different ranges of divergence. So this is conservation. Conservation is 1 minus the fraction of nucleotides that was substituted. And so this is data from many genes, and I align these genes so that the first position of the ATG start codon falls on 0. And so to the left of it is the 5' ATR, and to the right of it is the coding sequence. So you see that there are these species that have different rates of divergence and different levels of divergence, right? So this blue one is more closely related, and this cyan one is most distantly related. And you also see that the divergence is not uniform in the 5' UTR. There is this increase in conservation about 120 nucleotides upstream of the start codon. Does anyone have any idea of what this can correspond to? Why do we have this hill here? This local increase in conservation about 100 nucleotides upstream of the start codon.
Maybe some kind of operator.
Some kind of what? Operator? So this is yeast, these are eukaryotes. But yeah, so that is some kind of regulatory region indeed. So this happens just happens to be the core promoter, which is located in about this position in yeast. How about this comb that you see here in the opposite direction? Does anyone have an idea what's going on here? Why do I have this, these fluctuations of the curves of different color here to the right? What is happening here?
The second and third lecture, we usually sometimes.
Does everyone see what Alexei just said? So here we have the periodicity of the nucleotide sequence in the downstream of the start codon. So I said that 0 is the start codon, and downstream of the start codon you have this coding sequence. And what usually you get is that the first position and the second position of a codon are non-degenerate or two-fold degenerate. That is, many of the mutations in those positions will change the encoded amino acid. And the third position, there the mutations usually keep the amino acid intact. And as a result, what you normally see is this pattern of conservation. It's high in the first position, high, even higher sometimes in the second, low in the third. Then comes the second codon, high again, low. High, low. And you see this nice periodic pattern of conservation, which is exactly what we see here. If we blow that up, it will be more visible. Then you can do that on, if you have enough data, you can do this same thing with even higher resolution. And you can ask, well, assume I have a protein and I have a large alignment of homologous of this protein from many different species, say vertebrates. Then that allows me to look at individual amino acids and say, well, if an amino acid, say methionine, is very well conserved here throughout all these species, then this methionine is probably important. However, if some amino acid seems to be substituted somewhere, then it probably doesn't make much of a difference. And that allows me to annotate mutations as important and non-important, right? If I see a mutation in a very conserved position, if some position is very well conserved, then if a patient comes to a clinic, I sequence his genome, and he has some genetic phenotype. I sequence his genome, and in a gene that I think is likely to cause this phenotype, I see a change in such a conserved position, say in this position M is substituted by some other amino acid, then that is probably the mutation that has caused this phenotype. If I see a change in position like this one, then well, that's probably a neutral mutation. That's probably not a candidate driver. I probably go and look somewhere else. That's something I understand. That's something that you guys have been. That's the logic you have been using in the first computer lab, and also that's the logic that is still used by some of the state-of-the-art computer programs for annotation of human mutations, such as, for example, polyphen. So this, so the functionals will say that the functionally important segments of the genes evolve slowly, and exons evolve more slowly than the introns. Sometimes there are exceptions. Sometimes there are cases in which a variant is, say, we observe let's pick a good example here. For example, we observe a variant. Let's see here. Okay, so assume that we have this like last column, right? So assume that the first species is human and all the other species are non-human, and we have N in human and then D in all these other species. And then we can ask, well, how bad is the mutation from N to D in a human patient? And sometimes there are cases, so you would sort of assume that this would be a neutral mutation. After all, this D is encountered in all these other species. However, sometimes these mutations do turn out to be deleterious. Sometimes we see that the allele, say D, here in human, that is deleterious and bad and pathogenic in human is actually the wild type allele in other non-human species. That is something that people have called compensated pathogenic deviations, and the reasoning is that we think that this N2, so that D is allowed in all these other non-human species because it is somehow compensated by some other changes in the amino acids, perhaps in this same protein or perhaps even in some other proteins. So these compensations are something that I'm very interested in. That's something that people do not really know well how to look for. In fact, if such compensations are very abundant, that sort of puts a limit on how well we can do personalized medicine, on how well we can predict the patient's phenotype, tolerance to drugs, predisposition to diseases, and so forth, by just looking at the set of alleles that he or she has at his size. If this N or this D, say here in human, causes a disease, that's one thing. Then a doctor can do this panel and say, well, you have a D here, you are predisposed to a genetic disease. However, if the effect of this D here depends on all the different amino acids in all the other positions, that really complicates the life of for a doctor. One other way to detect negative selection, and perhaps let's stop here after I mention it, and that's something we have mentioned already, is that negative selection reduces the allele frequency. And we have seen this plot before. So we see that, so this is the distribution of the binary frequency for different variants and the fraction of loci carrying alleles at this frequency, and we can ask what is the expected allele frequency spectrum under neutrality. And we can write the equations for that, and it will be this red thing. But in real life, we see that non-synonymous alleles are sort of biased towards low allele frequencies. And in fact, even synonymous alleles are biased towards low allele frequencies, even though to a smaller extent. That means that, again, the selection prevents mutations from spreading to high frequencies, probably because many of these mutations are deleterious, and this effect is particularly noticeable for non-synonymous mutations. However, it is also visible for synonymous ones. So, basically, for negative selection is sort of easy to observe, right? It's just when you look at, you can just see it by simply looking at conservation. If you see some pattern of conservation, then that increased conservation is due to the action of negative selection, even though there are some caveats that we'll discuss later. What about positive selection? How hard is it to detect in the genome? And basically the question we are asking again is that if we see a divergence between two species in some amino acid, well, how did this substitution affect this? If you have increased it, kept it in variable, or reduced it, and we're interested in the fraction. Let's ask what fraction of substitutions genome-wide, say amino acid substitutions in protein coding sites, have actually been adapted, have actually increased fitness. And let's take some model organism that we are, that people have studied very intensely, such as a fruit fly here. And well, let's just go to the literature and look at the papers discussing this exact question. What is the fraction of amino acid substitutions that were adapted? So this is a paper by Tomoko Ota, who is the co-creator of the neutral theory. And she writes, no clear distinction can be drawn between the nearly neutral and the selection theory. That means she's saying that we cannot tell if any of the substitutions were adaptive at all, period. There's always some alternative scenario that does not involve selection that we can come up with. Well, maybe Tomoko Ota is biased. Maybe she's a crazy old woman because she has co-created this neutral theory. Maybe she's just very biased. Let's look at other people. So this is a Nature paper, right? A big, important journal, Nature, by Smith and Adam Walker. And here in the abstract they say 45% of all amino acid substitutions have been fixed by natural selection in Drosophila, in divergence of two Drosophila species. That's a good number, 45%. That sounds exact, right? Nearly half. So 2 years later, again, Adam Walker, the same second quarter, a not so influential journal, Molecular Biology and Evolution, similar analysis, similar species, not much of a difference, just slightly different analysis. They say, well, approximately 25 plus or minus 20% of amino acid substitutions were driven by positive selection. So to me, maybe these people were a little bit shy to say 25 plus or minus 25%. But to me that says that they do not really know whether there has been selection there at all or not, right? So finally, this is some more recent paper by Dan Hartle, again, PNAS, a famous journal, saying that about 25% of these differences are positively selected. So you now see that the estimates are all over the range from 0 all the way up to 25. So next Monday, let us start discussing why actually detecting adaptation, detecting positive selection is so hard, and what can we do about it? What are the approaches that would work? Thank you very much. And I'll